Hello, everyone. Welcome back to the AAS YouTube channel, and this is the good stuff. This is the AAS Author Journal Series, and I'm super happy to have Gloria Fonseca Alvarez with us today. Hi, Gloria.
Hi.
How are you?
Good. Excited to be here.
Good. What is your geolocation? Where are you at?
I go to school at the University of Connecticut, so around the Stores, Connecticut area.
Okay. Okay. So in the upper east of the U.S.
Yeah.
And you are a graduate student, correct?
Yeah, I'm about to start my 4th year of grad school.
Awesome. So you're all but dissertation.
Kind of, yeah.
Very good. Very good. How are things going pandemic-wise at your institution? Are classes going? Are people going in person, or what's this?
I'm kind of out of the loop since I'm done with classes, so I'm just working from home as I've been over the summer. But I think mostly hybrid classes. There's been some incidents, but that made the national news. But it's good.
I admire that you have a whiteboard there in your home office. I think that's pretty cool.
Yeah.
Very good. Awesome. So Gloria, what do you like to do for research?
I think generally I'm interested in all things black holes, but for my PhD, I'm working more on the sort of like the small scale, like supermassive black hole accretion disk area. So I'm a part of the SDSS-RM collaboration, as you can see, well, you'll see from my paper title. So I guess I also work on reverberation mapping.
Mm-hmm. Very cool. And in fact, that will take us exactly to this really lovely APJ article. So I'm going to pull it up, and we are going to cover the Sloan Digital Sky Survey Reverberation Mapping Project, the H-beta Radius-Luminosity relation. Gloria, take it away.
Okay, so as I said, I work with SDSS-RM, which is the Sloan Digital Sky Survey Reverberation Mapping Project. Mm-hmm. So the SDSS-RM is a multi-object, multi-year reverberation mapping campaign that has been observing, time monitoring about 850 quasars from the Sloan Digital Sky Survey over the past 4 years. So this paper in particular was motivated by a 2017 paper, which was the first data released from this project by Greer et al. And that paper, they published 44 H-beta lags from the first year of SDSS-RM. And in that paper, there was a figure that showed the relation between the radius of the broadline region and the optical luminosity, which is the luminosity relation. And when we look at the radius-luminosity relation for the SDSS-RM data for H-beta, we find that it's different than the established radius-luminosity relation.
That was a nice way to say that. That was a nice way to say that.
Yeah. So after that paper, I guess the idea for this project came up since we thought that it merited its own paper rather than just like a section of a paper. Yeah. And so I guess the idea for this paper is basically trying to figure out if this discrepancy between what we see and sort of like the Benz et al. Relation, if it's a real thing, if it's just like observational biases, or if this depends on quasar properties. So that's what I tried to answer, and I think determine it's probably a real thing, and it probably depends on likely the UV optical SCDs. So if you go to the first figure, I guess I can.
Slide to figure 1. I'm going to blow this up, people.
Yeah.
Okay, figure 1, RL.
Yeah. So for this paper, we work with 3 different samples of reverberation mapped AGN. So this is just a figure of the radius luminosity here shown as a time lag, and the luminosity is the AGN optical luminosity at 5100 angstroms. So the radius-luminosity, the Benson-All radius-luminosity relation that I mentioned is shown here as the black line with the data that were used to determine that relation, shown also in black.
Okay.
And okay, so the SDSSR endpoints are shown here in red, and if you can see that, okay, some of them fall on the Benson-All relation, but some of them, like particularly on the lower right, have lags that are quite a bit shorter than what we would expect based on the relation.
Yep.
Yeah. So, and also interestingly enough, another group that's not related at all to SDSSRM, the CMBH collaboration, that's the super Eddington accreting massive black holes collaboration,
okay,
also finds this trend of having smaller lags than expected based on their luminosity. So those are the points shown in blue. Yeah. Now their sample is a bit different since they were specifically targeting highly accreting quasars. So yeah.
Okay.
Yeah. So if anyone is unfamiliar with this relation, so the radius-luminosity relation allows us to basically measure black hole masses from a single luminosity measurement, right? So these are what we call single epoch mass measurements. So reverberation mapping gives you the mass of the black hole from like time ordering, which is expensive and it takes time, and is also not necessarily possible to do at high redshifts. So a lot of the black hole masses that we have actually come from the radius-luminosity relation. Okay. So it's important for us to know whether or not we have the correct radius-luminosity relation without any like biases. So
cool.
Yeah. So I guess the first thing that I did was sort of like a sanity check to make sure that this wasn't some like silly mistake or something. So the first few figures are just like, well, the second figure is just like the distribution over sample, which isn't necessarily.
Okay.
Yeah, I don't really need to talk about that. Okay. So figure 3 just shows the radius-luminosity relation from that was already in the Greer 2017 paper. So here we show the 44 H beta lags in red, but also we show these open points, which are just the same data, but without removing host galaxy contribution. So we wanted to see if, okay, let's assume that we were doing the host subtraction incorrectly. This could move the points to the left, and therefore they would fall in the Benson-All relation, right?
Right.
But we can see that even when you don't remove the host subtraction, you don't automatically, fix everything. So that was one thing we checked. And then also to further check that this wasn't a host subtraction problem, in figure 4, we show.
One question here. What are the yellow squares?
Okay, so the yellow squares are 2 points that we excluded for 2 reasons. Okay. One of them was just the longest lag that we had. So it's kind of like an outlier, and it had like very small uncertainties compared to the other points. So we excluded that. Yeah. The other point is a hyper-variable quasar. There's a paper by Dexter et al. That talks about it. But since some of our analysis later on in the paper uses data that was published a bit later than the observations for the actual lags. So we didn't want to like contaminate things, since that quasar varies in luminosity by a factor of 10 over that time. So we just excluded it from our analysis. Yeah.
Okay, thanks.
Yeah, so this figure is just, since the H beta luminosity should not have any issues with host contamination. We wanted to check that if we, use the H beta luminosity instead of the optical luminosity, the 5100 luminosity, that we still saw the same trend. So this is not being compared to the Benz-et-al relation, since they didn't have an actual relation using H beta. So we just used a relation from Caspi et al. And we, again, see the same offset in some of our points. So then I kept on trying. And another thing that we wanted to make sure is that the way that we measured lags wasn't affecting what we observed. So figure 5, I believe.
Okay. Go back to that one. Figure 5. Yep.
Yeah. So the Benz-et-al sample is sort of like it's a compilation of different, I guess, RM campaigns, but they usually use ICCF to measure the lags. And for the Greer et al. Paper, we also had the ICCF lags, but in this paper, we used the lags that we got from Javelin and Cream, not ICCF. So we wanted to make sure that it wasn't just this. So here we just show the radius-luminosity relation using the ICCF measurements instead of Javelin. And again,
and remind me what ICCF stands for?
ICCF is the interpolated cross-correlation function.
Okay.
Yeah, so ICCF and Javelin should give you the same results. There's some differences in the way that they calculate the lag and the assumptions that it makes. Okay. And there's been, well, there's another paper by someone in our collaboration that found that at least for our data, Javelin produced better results than ICCF. So I think, and again, I don't think there's an issue using a different way of measuring lag, since we still see this.
Okay.
Yeah. Okay. Right. So the next thing that sort of like the next step was to sort of like see if observational biases could reproduce this this discrepancy.
Okay.
So that's all the way, I think, figure 8, 9.
Figure 8. Okay, moving. Figure 7, figure 8, figure 8. Okay. Now which one? Figure 8?
Maybe figure 7.
All good. Figure 7.
Yeah. So what we did here was just a Monte Carlo simulation of a radius-luminosity relation, just based on the, if we take, I guess, a general population of quasars, okay, and we predict the radius of the BLR based on the Benz-et-al relation, and we add what we think is our observational biases, like, for example, the longest lag that we can detect and the shortest lag that we can detect. And also we have a magnitude limited sample. So if we add those things in, could we reproduce the observed radius-luminosity relation, which has a slope of like 0.24 compared to Benz-et-al, which had a slope of 0.5 around. So we did this for a lot of iterations, and that's what figure 8 shows.
Okay. Yeah.
Yeah. So since I forgot to say that we also included the sample size, since we have 44 AGN, and selecting, I guess, different AGN gave us a different result. So we decided to have a distribution rather than just say, oh, a single simulation is going to answer everything. So here, it just shows the distribution of slope and normalization from just fitting different simulated radius-luminosity relations. And it just shows 3 different slopes and normalization. The point in black is supposed to represent the Benz et al. Results. The point in red is what we measure for just the SDSS-RM data.
Okay.
And the point in dark red at the top is if we, instead of assuming that there's a different slope, if we just assume that that our data can be fit by the same slope of 0.5, and we just have an offset in normalization. So that's what that dark red point is. And from this, we see that it's consistent. Our results are consistent with Benz to 2.5 sigma, okay. And our point falls outside of 3 sigma. So, and we also repeated this with more lags. So I think this year we have the upcoming SDSS 5, which will be monitoring about 1,000 quasars, and we expect that this will increase the number of detected H-beta lags from the 44 that we have to about 100. So this is just the same simulation repeated, but for a larger sample. And we expect that this would better constrain whether or not we can reproduce this.
Let me ask a question on this one. Is it a concern that all of the data points are sort of outside the red colored contours?
For
not totally outside, but they're not in the middle.
No, they're not in the middle. Yeah, so it's that's why I said it's probably not. But
okay.
So but I think for this we were just like, okay, it's more consistent with the Benz than with our data, and yeah.
Okay. Yeah. Thanks.
Also, there's another. I also mentioned a simulation earlier from another member of our group. She, for a different purpose, also did a simulation, and she also found that you can't exactly reproduce what we observed just based on if you just add observational biases. So,
okay.
Yeah.
Very good.
And so this was, well, in a way unexpected, but also not.
Okay. In what way was it expected?
Well, I'm sorry.
In what way was it expected?
It was unexpected because well, you have this established relation, and here we go with this new data, and it's different. So, but I mean, and I guess it would have been a less interesting paper if we just found, oh, hey, like,
same.
it's just observation biases. But I say unexpected because, so one of the advantages that SDSS-RM has is that, it's multi-object. We just like stare at a patches of sky, and we just, whatever we get, right? So it's just the only selection we did was a magnitude limit, whereas other samples may have been biased to a particular type of quasars, like if you select by like highly variable quasars, because it's easier to do reverberation mapping on if you have a lot of variability, or like, for example, if you have the CMVH sample, which was specifically selected to be highly accreting things.
Okay. So,
and from previous papers, like from just a description of SDSS, if you look at the eigenvector 1, which is just a figure if you have full width half max of H beta versus the relative iron strength, which is just the ratio of the equivalent width of iron 2 over H beta. If you look at the figure, which has been found to show sort of like a diversity of quasar properties, and you include the previously published catalog of reverberation mapping quasars, you see that they occupy a specific area of the eigenvector 1, and if you also include the CMVH quasars, they occupy a small area, sort of like on the highly accreting area. But the SDSS-RM sort of like fills the middle and also occupies sort of like a broader area of the eigenvector 1. So we would think that this sort of like has a more general population of quasars than previous things. So we would, I guess, expect it to not be just observational bias like that.
Right.
But the next thing that we did was, well, if it's not just that, then does this offset depend on any quasar properties? And I think a popular thing is the accretion rate. So
Yep.
yeah, and here we show the accretion rate calculated by two different dimensionless quantities. The first one is the Eddington ratio. And the second one is just M script, which was a quantity described by the CMBH collaboration. We just include this so that we can better compare to the results.
It's a ratio. Okay, I'm with you. I'm good. Yep.
Okay. Yeah. So so let me describe, I guess, the axis on this. So I have it's a log, and it's tau observed, which is our measured lags, and tau RL, which is what we would expect if we just calculate it from the Bettel radius-luminosity relation.
Okay.
So it's supposed to signify how offset our points are from that line.
Yes.
Yes. And here we include all three data sets. So again, black is the Benzodol sample, red is our sample, and blue is the CMBH sample. Yeah. And we do find a correlation between the offset and accretion rate, which is sort of, I guess, there's other work that, like particularly CMBH, that I guess is trying to explain this offset just based on the accretion rate. But so their results, as I've said several times, they selected higher accreting quasars. So I guess that would be sort of expected. And also, if you write everything out here, like in the little equations, you will see that the Eddington ratio, as it's calculated by the volumetric luminosity, which we don't actually have, we're using other luminosities.
Right.
Also has the Eddington luminosity, which depends on mass. And that mass is calculated using the lag that you see on the y-axis. So there's some, I guess, some autocorrelations there in this particular type of figure. So, so I guess we would expect there to be a correlation, even if there isn't actually. So, but that doesn't exclude there being a correlation. So we tried other things, other independent ways of measuring accretion rate. So the first thing that we tried was if you break up the accretion rate into all its, I guess, parameters. There's the line width, which does not depend on the mass or anything that you find on the y-axis. So we tried to see if there's a correlation between offset and line width, which we show by two different measurements: the full width half max and sigma RMS. And we don't find a correlation with those things.
Okay.
So another thing that we tried was the relative iron strength. So that's figure 11.
Okay. Yes.
Yes. So the relative iron strength, which I described earlier, has been shown to be correlated with the Eddington ratio. And this is independent of backend mass. So we tried to see if there was any correlation. And unfortunately, we don't find one. The CMBH team does find a correlation with relative iron strength, but yeah, this could be because we might have too small a sample to really see this. So like this eigenvector one relative strength accretion rate trend included a lot more objects than we have here. So maybe that's why, but yeah.
Does the other team find a strong correlation?
Yeah.
Okay.
Yeah, it's right at the top, right. They find a.
Oh, got it.
Yeah.
Okay. Oh, yeah.
Is then with 0.
Okay.
But again, they have
Quite strong.
a particular sample. So.
Yes. Okay, I'm with you.
So another thought that we have, which was partly inspired by work by Cherney et al., 2019, was, well, you have a radius-luminosity relation for the broadline region that is based on the optical luminosity, right? L5100, whereas the actual location of the broadline region is based on the ionizing luminosity, which is not L5100, right? And Cherney et al. Has in some modeling of the radius-luminosity relation by determining the location of the broadlight region using the ionizing radiation, they're able to reproduce some of the trends that we observe. So we wanted to investigate if, okay, is this offset related to the ionizing luminosity and the UV optical SED shape. So if you have changes in the ionizing luminosity, but that don't change in the optical luminosity, then you could see some offsets here. So we tried a few things to see if going maybe closer to the UV.
Oh, right. Mm-hmm.
Yeah, sorry, and I guess I didn't mention the color coded tops of the figures. That's just the radius luminosity color coded by different parameters. Here it would be like the two luminosities that we're looking at here. So we just tried to see if H beta or L3000, which were closer to the UV, if there was any correlation, and there is not.
Okay. Okay.
And so, yeah, finally, the best thing that we found, other than the accretion rate, was a correlation with the ratio of the O3 luminosity and H beta luminosity. And that's in figure 13. And we use this since it can be used as a proxy for the ionizing radiation, and we see that there's actually a correlation.
Okay. Okay.
Yeah. So I guess we think that so the SED shape depends on several things like mass, accretion rate, spin. So we think that depending on for each object, it could have a different SED shape, which would be causing it to, I guess, have a different radius luminosity relation. Yeah.
Okay. Awesome. So what do you say is the takeaway?
Well, takeaway, I guess, would be radius luminosity relation is important because it helps us learn most things about black holes. And it's not entirely a settled matter. Like, it's not just, we have just the luminosity and that's it. And I think there's some work being done to try to correct just like the radius luminosity relation. That's not what we were trying to do here. Yeah.
Okay, very good. So where do you let me follow that on. So where do we go from here, given what you published? What would sort of be next steps? Seems like we have a few mysteries to wire out. So where do you go? Where does the community go over, let's say, the next 3, 5, 10 years?
Yeah, so we actually have a couple of different things that we could do. So one, we have a upcoming program from HSD where we can actually create a radius luminosity relation based on UV luminosity, which, like I said, it's actually what's actually affecting the broadline region. Yeah, so we could attempt to create a new radius-luminosity relation based on the UV. That's one thing.
Okay, cool.
The other thing, which is what I've been more involved in, is so we have, thanks to the fact that we use, SDSS, we have a lot of multi-wavelength data that is public already. So we can actually create contemporaneous UV optical NCD. So this would be based on pan stars in the optical. We have XMM. We also have WISE. And also Galax in the UV.
Okay.
And at least for Galax and pan stars, there's a lot of contemporaneous observations. So, and contemporaneous just meaning like within a few days up to a week. So we can actually measure a lot of the things that we're kind of assuming in this paper. Like we can actually measure an accretion rate. We can measure an actual metric luminosity amongst other things. And we can also see if we think if it's just like the NCD shape that could explain some of these offsets. So yeah.
Very cool. Very cool. Future's bright. Lots of things to do. It'll fill out your graduate student trajectory. Absolutely. Gloria, I want to thank you so much for spending some time today and walking us through your really lovely paper. And for those of you who are interested in following up, you can reach out to Gloria. We won't be putting her email address in the YouTube video or in the description below, but you'll know how to get in touch with her. So Gloria, thank you so much. Okay, everyone, that will do, and we will see you on the next one. Bye-bye.